And we're assuming the plates are large. Now, of course, I mean, if you come near the edges, there will be like a fringe field. Like it's not going to be straight. But if they're truly infinite, then the field will just be from the plus to the minus. Anywhere outside it is zero. Okay. If that's okay, I'm going to go on. We're now make a small calculation just to familiarize ourselves with this parallel plate. I'm going to write down the problem or the example. And how am I doing? Yeah, I'm still okay. So here is the example. We have two parallel plate capacitors, and they are 1 centimeter by 2 centimeters. The length is 1 centimeter, the width is 2 centimeters, or the length is 2, the width is 1, and then the distance between the plates is 1 millimeter. So, in other words, so you have a parallel plate capacitor, or a parallel plate capacitor with dimensions 1 centimeter by 2 centimeters, and the distance between the plates is D equals to 1 millimeter. Distance between the plates is 1 millimeter. Now it says, what should the charge on each plate? What should be the charge of each plate? What must be the charge on each plate so that the electric field will equal to 2 times 10 to the 6 newtons per coulomb between the plates inside the capacitor. So what must the charge be to produce such an electric field? So I think we can answer. What can we do? What can we do?
Find the force in one of the plates.
So we find we have the electric field.
Yeah.
This is a parallel plate capacitor. The electric field is E equal to Q over epsilon naught A, right? So I'm going to, inside, it's Q over epsilon naught A. So, solution. Electric field inside is E equal to Q over epsilon naught on the area. Since I'm looking for Q, so for Q. Epsilon, yeah.
Where does the 2 next to the epsilon go? Because you have written there that says E equals E plus minus eta over 2 epsilon.
Yeah, the electric field due to the pluses only is eta over 2 epsilon naught, and the one due to the minuses only is also eta over 2 epsilon naught. In between the plates, the minus and the plus, they point in the same direction.
Okay.
So the total field would be the addition of both, so the 1/2 of both.
Okay.
Yeah, good question. Yeah. And outside, they just cancel, take that out to 0. So we need to plug in some numbers. So Q, epsilon naught 8.85, right? Times 10 to the minus 12. The area is length times width, so it's a 1 centimeter by a 2 centimeter. Don't you work with centimeters, right? You want meters, because epsilon naught has units of Coulomb squared over Newton meters squared, so you want to be in meters. Yeah.
Is it a 1 meter? Oh my god. No.
Oh, the distance between the plates is 1 millimeter.
1 millimeter.
Oh, by the way, we won't need it. We won't need it. What we want is the area of the plates, right? That's what we need, the area. So the D over here refers to this distance from here to here. But what matters is the area of the plates. So let's say this one is 2 centimeters by 1 centimeter.
The distance can be any number.
The distance, well, in principle, yeah, if they're truly infinite, but usually for a realistic parallel plate capacitor, you want D to be very small.
Isn't there usually insulation in between the two?
Yeah, yes, usually have a dielectric. Yeah.
Okay.
Yeah, because if you have a conductor, they will just get discharged right away.
And air can be kind of.
So, yeah, we will work on that later. Yeah. But you're ahead.
Okay.
Yeah. So Q, and then the area is 1 centimeter by 2 centimeters. So 1 centimeter, so 1 times 10 to the minus 2 to change it to meters, and then times 2 times 10 to the minus 2. That's the conversion of 2 centimeters also to meters. And then the electric field is the 2 times 10 to the 6th power. So Q, do I have Q? Yes, I do. 3.54 times 10 to the minus 6, or minus 9, sorry. Minus 9 coulomb.
For units, how did you get Coulomb top?
For which one?
For your units, how did you get Coulombs at the top? Because the right side is Newtons over Coulombs, right? 2 times 10 to the negative 6.
This one?
Yeah.
You mean left side?
But the 2 times 10 to the negative 6?
Yeah.
It's Newtons.
For Coulomb, yep.
Yeah.
And this one is meters.
And then.
And this one is meters. And this one is Coulomb squared per Newton meters squared.
Oh.
Yeah, so this one has some units to it. So the units will work out to be coulombs overall for the change. Yeah.
Just a question to clarify, for the infinite sheets of charge, it doesn't matter how far away you are from it, the energy field is going to be the same.
Yes.
Can you explain again why that is?
The simple explanation is the math tells us so.
Okay,
But
that's
then,
yeah.
the physical, no, seriously, it is the math, that's how we derived it, truly.
Yeah.
We wouldn't have known that it's actually constant.
Okay.
But then once the math tells you, then you try to come up with a physical explanation and say, okay, yeah, of course, it makes sense, right? And then you say, okay, if you get really close, the physical view is, if you get really close, you're affected by few charges.
Got it.
These will not matter much to you if you're like really here.
Yeah.
But if I get farther, more charges come on my view.
So it's proportional.
Yeah.
Okay, that makes sense, thank you.
And so it ends up, you go farther, more charges come up, and then they will just cancel the farness with the more charges, and it just keeps the field constant.
Okay, that's
Yeah.
good, thank you, that makes sense.
Yeah, yeah. But truly, the honest answer is we would guess that, but we wouldn't know that they would just cancel just enough to keep it constant. The math we have to do the math. Yeah. Yeah.
Doesn't that only apply for like infinite plates though?
Infinite, yes.
So then in this case, why isn't there a distance being factored in?
Because it is, so that's the key. The plate area versus the distance between them. Distance between them is a millimeter, and the dimension of the plates is like 10 times that or 20 times or whatever. So it is much larger in this area than in this direction between the plates. So strictly speaking, it is an approximation, it's not exact. But we always idealize, we say, let's assume it's infinitely charged. It's like the ideal gas law, right?
Right.
Yeah. Good questions, and but just operationally, does it make sense how I'm using this formula here and all that stuff? Okay. If I say how many electrons are needed to make up this charge, what would you do?
So
Divide by
Q.
electron.
By the charge of an electron, right? Yeah. And you will need a large number of electrons. I think it's like 10 to the 10. 10.
Yeah.
Okay. Now, the next topic is motion of charged particles in an electric field. We have been producing an electric field, but then once it's produced, what does it do for charges? Or what does it do to charges? So, suppose I put a charge in an electric field. Okay? I put a charge in an electric field. Motion of charged objects or particles in an electric, right? Charges in electric. First of all, if it's neutral, it doesn't care about the electric field, whether it's there or not. Now, if it is charged, then it will experience a force. The force on a charge in an electric field, suppose here's an electric field. Here is E. An electric field this way. That's the electric field in this some direction. And I put a charge Q here. Suppose I put a plus Q. What would happen to it? Will it accelerate to the right or to the left? Would accelerate to the right. And here's how you should think of it. Whenever I say, first of all, let's say I have an electric field going to the right. If I say, how would you produce such an electric field? Give me a setup that will produce an electric field like this for me. You should know now. We just figured out a way to set up an electric field to the right.
So from a positive plate and a negative plate.
Good. Parallel plates, they will produce for you an electric field this way. The positive plate should be here, the negative plate would be here, that will produce an electric field to the right. Good. So if you see an electric field to the right, feel free to think, here's a positive plate here probably somewhere producing it, or maybe a negative plate here, or maybe both are present. So if you have a positive plate here, what do positive charges do to positive charges?
Repel.
Push them away. So it will experience a force this way. But if it's a negative charge, well, there are pluses here producing this electric field, so it will be attracted. So the force on a charge is the charge times the electric field, right? Remember how we defined the electric field? Was the force per unit of charge? So that is that. Now, I know from Newton's second law, if the only force on a charge is the electric force, then the net force is equal to this electric force. And F equals to what? By Newton's second law?
MA.
MA, yeah. The mass times the acceleration. And so I would figure that the acceleration would equal to, divide both sides by the mass, so you get Q over M times the electric field. Right, F equal to M. And we just needed to recall the relation between the force on a charge if it's sitting in an electric, just Q times E. Magnitude of the charge times the electric field would be the magnitude of the force. Any questions on that? Yeah.
So, if you say your electric field is going in one direction, you assume that it's going in the positive, the referencing the positive plate?
If I say electric field going to the right, I can think of, maybe I have pluses here producing that electric field, or equivalently, I can have minuses here producing that same electric field, or both. I can have both. good picture to keep in mind, because if you're ever confused in what direction will the force be, think, if it's a plus, electric field is this way, who produces electric field this way? Well, it's maybe pluses here. Pluses, they will repel pluses. Or if you like this picture of the minuses, well, minuses want to attract the plus, so that effectively will also make it go to the acceleration. Okay? So, let's do a couple of examples, actually. It says two 6 centimeter diameter electrodes. So an electrode means a plus plate and negative plate. So let's say it's a 6 centimeter. Sorry, here is an example: a parallel plate capacitor. By the way, do the plates have to be rectangular?
No.
No, as long as it's large enough, it's an infinite sheet. It could be, in fact, the way we derived an infinite sheet, we let R go to infinity for a disk, right? It became an infinite sheet. You could have circular plates, and their area would be pi r squared. So, a parallel plate, capacitor. Is made of two discs, each has diameter, has a 6 centimeter diameter. Okay? And then the charge on each plate is 10 to the 11 electrons. And we did the 10 to the 11 electrons. We found this, right? The charge on each plate is 10 to the 11 electrons. Charge on each plate is made, basically, one of them is plus 10 to the 11 electron, one of them is negative 10 to the 11 electrons, and the other one is a positively charged of equal amount. So basically, if you take an electron from a plate and place it on the other, this one will become net negative, and the one that lost an electron will become net positive. If you lose an electron, you become a net positive. The charge on each plate is let's just write it down. It's Q equal to 2.04 times. I'm sorry, 1.6 times 10 to the minus 8 coulombs. That's the charge on each plate. One of them is plus charged, the other one is negatively charged. Okay. So that's the situation we have. Here is a positive. And here is the negative. And again, I'm exaggerating the distance between them, because if I put them too close, I can't really draw anything in between, right? So I'm exaggerating the distance. So in what direction would the electric field be?
To the right.
To the right. The electric field would just be this way. That's the direction of the electric field. Suppose you place an electron and you let it go. Okay? Place an electron and you let it go. So first of all, if I put an electron right here, what happens to it? It's stuck. I mean, it's where it wants to be, as far away from the negatives as possible and as close to the positives as possible, right? Electron is negatively charged. That's where it wants to be, so nothing happens. Well, if nothing happens, then the problem is solved. Then we don't have a problem to solve. So we want to solve a problem. So we will put an electron right here. And the question is, how long will it take the electron to hit this plate, to get to here, assuming that the distance between them assuming D is 5 millimeters. 5 times 10 to the minus 3 meters. How much time will it take the electron to get to here? And then what would the velocity of the electron be, or the speed? What would the speed be? So, well, I have to find I need the acceleration, right, to do kinematics. I need the acceleration. To find the acceleration, I need the electric field. I will eventually need the mass of the electron and the charge of the electron. Those are things they're constants that we can look up in the book. And so, the electric field we have to find first. Okay, so what should we do to find the electric field?
Q over area.
Yeah, Q over area, to find eta, and then, or you can put Q over A and then epsilon naught, right? So let's find the electric field. Electric field will have a magnitude of capital Q divided by epsilon naught times the area. Q is the charge of each plate, and we said the charge on each plate is S 1.6 times 10 to the minus 8. So 1.6 times 10 to the minus 8 divided by epsilon naught, which is 8.85 times 10 to the minus 12, and then the area. The area of the plates is pi r squared. The area of the plates is pi r squared, so pi r squared. What is the radius of the plate?
0.00005.
3 centimeters or 0.03 meters, right? So this is the diameter. Diameter is 6, so the radius is 3. So 3 centimeters, that is 0.03 meters. So let's find the electric field.
Square.
Squared. Yes, right. Turns out the electric field would be about 6.4 or 6.39 times 10 to the 5th. 6.39 times 10 to the 5th. What units of electric field? What are they?
Units per coulomb.
Newtons per coulomb. That's the electric field. Now I need to find the force on this electron, right? The force, if the electric field is this way, the electron is negatively charged, so the force on it will be that way. Again, you can think of it in two ways. Mathematically, you're multiplying a negative number by the electric field. So a minus times the vector that reverses the direction of the vector, so the force will be this way. Or, think of it, I like to think of it in simple terms. I have minuses here. Minuses do not want the minus next to them, so they will push it away. So the force will be this way. And pluses, they want that minus, so they will attract it. So the net force would be this way. That's the direction of the force. That's the direction. Now, the magnitude of the force would be just Q times the electric field. Again, magnitude. What's the magnitude of the charge of an electron?
1.6
1.6.
on 10 to the negative 19.
19, yeah. And so good, we're getting familiar with those numbers. And this one is 6.39 times 10 to the 5th. Let's please get the force. This.
It's 1.02 times 10 to the negative 13.
13? Think so? Thank you. Newtons, right? The force.
Yeah.
Yeah, sounds good. So 6.39 times 1.6 is about 10, right? Okay. Yeah. Good. Yeah, so we found the force. Next, what do I do?
Find acceleration.
Yeah, F equal to ma. That's the only force on this electron is the electric force. So the acceleration would be the force divided by the mass, right? So the force is 1.02 times 10 to the minus 13 newtons. Does anybody know what the mass of an electron is?
Something negative 27.
A proton is something times 10 to the
9.81.
31, yeah.
Oh,
It's,
31. Oh, yeah.
It's 9.11. Yes. Times 10 to the minus 31. That's the mass of the electron. I mean, you're not expected to memorize it. I will give it to you if you need it. In the homework, look it up. If you need it. It's a good number to have down. So the acceleration would turn out to be 1.12 times 10 to the 17.
What?
Okay.
Meters per second squared. That's the acceleration.
What's the speed of light?
This is acceleration, so speed of light is 3 times 10 to the 8 meters per second. So we get the speed of this thing. So this is the acceleration. The acceleration, how do I find the time? We can use kinematics, right? X final equals to x initial plus v initial times the time plus 1/2 times the acceleration times the time squared, right? So you can write like this, x equals to x initial plus v initial times the time plus 1/2 of the acceleration times the time squared. Let's assume the initial position is the 0. That's the origin of our coordinate system. V initial is released from rest, so that's also 0. And so I just get the distance traveled from here to here is equal to 1/2 AT squared. So the distance traveled is equal. So again, this is 0. It's released from rest, so that's 0. So the time would just be 2x over a square root, and x is this 5 times 10 to the minus 3. So you get 2 times 5 times 10 to the minus 3 over a. The acceleration is 1.12. 17 square root. So the time would be short or long?
Short.
Very short, yeah, it would be short. About?
I got 2.98 times 10 to the negative 10.
Yes. So about 3 times 10 to the minus 10, right?
Yes.
Yeah. That's the time. And now the speed. The speed, we know from kinematics what? V init final equal to V initial plus AT, right? Plus AT. V initial is 0, so you just multiply the acceleration by the time. So V initial is 0. So the acceleration times so the speed would be something times 10 to the 7th power.
3.36.
Yeah, about 3.3, 3.4. 36, you said?
I'm just basing it off that.
Okay.
3.36.
Something times 10 to the 7th. So that is that. And since we're at the same problem here, let's continue with it. If you keep all decimals, I think it turned out to be what, 3.34. So, anyway, it's that. Something close to that. Okay. So that's our electron. And now we're going to use this setup along with another setup to figure out. You see the electron here will move straight, right? So suppose I'm going to use this setup. So here's the setup. I'm going to just, I want my electron to move to the right, just to make life slightly simpler. So here is the setup. So here is the next example. So suppose I'm going to use this same setup, but I'm going to put the negative plate here and the positive plate there. So here's what I do. So I'm going to put a minus here. Minus. Here's plus. And our electron will start here, right? Here's our electron. When it gets to here, at what speed is it moving?
0.
Huh? If it hits the plate, it will stop. But before it hit, right before it hits the plate, what was the speed?
It was 1 or
3.36 times 10 to the 7th, right? So suppose so the electron will be moving this way. Suppose I make a small gap here, right? The electron will be moving like this. 3.36 times 10 to the 7 meters per second. That's the speed. Meters per second. And then, so I have produced a charge that's moving to the right. It will be going that way. Okay. And then I would turn the plates off. So, and now I have plates that look like this. Or is it? Yeah, I want the plus. It doesn't matter, but let me put the same setup as in the book. So here's a plus plate, and here is a negative. Okay. So in summary, here's what we have. We use these two plates to produce an electron moving at this speed. And now we're going to use this electron and run it through these two plates. So let me just draw these two plates now by themselves. So here is the plus, here is the minus, and here is my electron. My electron starts here, moving at the speed 3.36 times 10 to the 7th. When it gets to here now, so it starts here, when it gets to here, how would it be moving? Is it moving slightly upward, slightly down, or straight? It would be moving, yeah, it would start curving up, right? Why does it curve up? Well, there are pluses here, they would attract it. And minuses here, they would repel it. And so there is an electric field downward, so there would be a net force upward. So that the electron will actually go like that. The question would be, what's the final velocity? For this one, let us be careful. Let's draw a coordinate system. Let's say here's the x, and here's the y coordinate system. Okay, here's the x, here's the y. And I'm going to tell you what the electric field between the plates is. So suppose the electric field is 5 times 10 to the 4th, right? We have an electric field here. Electric field is 5 times 10 to the 4th newtons per coulomb, and it's in the negative j hat direction, right? Down the y-axis. Right, it's downward. This is my positive y upward, negative y down. So let's figure out what the force is. The force would be the charge times the electric field. So now, since I'm dealing with vectors, I'm going to write the the fact that the charge is negative, right? So this is already negative, the electric field is negative. The charge of an electron is negative, so minus times minus will give me
Positive.
a plus. So it will be positive, and so we'll end up with 1.6 times 10 to the minus 19. That's from the charge of an electron, times the electric field, which is 5 times 10 to the 4th J hat, right? Again, technically there is a minus sign here and there is a minus sign here. From the charge of the electron, it's negative, the electric field is negative, J hat. Minus times minus becomes a plus, and then we just write positive J hat. So in other words, the force is this way. Force is up. So the force, we will find it. The force ends up being, well, I don't have the force, so I will give you help.
9 times 10 to the negative 15.
How much?
9 times 10 to the negative 15.
1.6 is, times 5 is 9?
Oh, yeah.
I don't know, yeah, 8, yeah, I guess 8, yeah, 8. Yeah, 8. Times 10 to the minus what? Yeah, 15?
Yeah.
Okay. J hat? Please double check me. Sounds right, yeah, minus 15, yeah.
Is the blue arrow in the second diagram the electric field?
This one?
Yeah.
That's the electric field, yeah. Electric field is down. Yeah.
Why did you choose the electric field to go from positive and negative? Is that just like a given?
The electric field always goes from plus to minus.
Okay.
Yeah. Yeah, electric fields originate from pluses and they terminate in minuses.
Okay.
So that is the force, and now let's find the acceleration. The acceleration will be the force over the mass, right? Because it's the only force we have. You might say there is maybe gravity, negligible compared to all the forces we have. The force is this 8 times 10 to the minus 15. 8. No, not 8. The mass of the electron, 9.11 times 10 to the minus 31 J hat. So you get an acceleration of 8.78 times 10 to the 15. 8.78 times 10 to the 15. It's an acceleration, so J hat or meters per second squared in the J hat direction. So again, how does this compare to acceleration due to gravity, which is 9.8? The gravity is completely negligible, so we don't worry about it. Right? Just 10 to the 15, it's just way much. Okay, so that's the acceleration. So what would the final velocity be? I know that the velocity is v initial plus the acceleration times the time, right? Times the time. Now, how much time would it take it to travel from here to here?